As we go throughout this, I have color-coded my answer choices with green, orange, or red to determine the difficulty. I would say a very easy question that I think all of you should be able to get on your own is called a layup. There are some of asterisks on these where I might call it more of a slam dunk because it is very straightforward. We'll get to those. There's a couple three-pointers where, yeah, you can get these, but they're not as easy. And then maybe one or two half-court shots where there are a lot of room for error and maybe some sort of rules you have to remember quite a bit about. But notice a lot of this exam is what I would call a layup. And I hope from me explaining my thought process for a lot of these problems, I hope you agree. For the first one, we have the antiderivative of x squared divided by 4 dx. I would recommend anytime you have something like this, you can always write it as 1/4 and pull the 1/4 out to the front. Remember, when we anti-differentiate, we add 1 to the exponent and pull the reciprocal of that new value out front. And when you simplify, you get choice B. This is a very quick multiple choice question, definitely a layup. Which of the following is an equation of the line tangent to the graph y equals cosine of x at x equals pi over 2? So I'm trying to create a tangent line, and so I just start to write out either point slope form or slope intercept form, a line to represent this tangent line. You're welcome to pick your preference. I show the work for both of these. What I want to do is find how steep the cosine function is at this time. And so I take my y function and differentiate both sides to get that y prime equals negative sine of x. I input the time that I care about, and we get that the sine of pi over 2 is 1, and the opposite of that gives me negative 1. Really make sure you have a good grasp of your unit circle. We have pi over 2 here being a 90-degree rotation where you are on the y-axis, a y value of 1, which is why this comes out to 1. So I have a slope. All I need now is a coordinate, and so I look at this equation and say, well, when x is pi over 2, what is my y coordinate? And so you just plug pi over 2 in, and the cosine of pi over 2 is 0. So the function I'm working with has the coordinate pi over 2 comma 0, and the tangent line at that coordinate is negative 1. You put all this together in point slope form or slope intercept, and you get your tangent line, choice C, layup. Number 3 is a problem where you have to do the chain rule twice, and I'll walk you through why it's twice. Keep in mind that the derivative of the sine of something is the cosine of that same value times the derivative of that inside, so u prime in this case. So we have a 2, which is not doing any harm. I take the derivative of something squared. The 2 comes out to the front. It ends up here. I leave the inside the same. And then here is your first chain rule, where I take the derivative of the inside. The derivative of the sine of something is the cosine of something times, here's your second chain rule, the derivative of the inside. I'd recommend writing this as x to the 1/2 so that when you remove 1, you get x to the negative 1/2, and that 1/2 ended up coming out front. And if you rewrite this, the 1/2 times the 2 will cancel. The x to the negative 1/2 will become an x to the positive 1/2 in your denominator, and you get choice D. The fact that this has a double chain rule, I would call this a 3-point shot problem. Number 4 is a U substitution problem. Shout out to Soldier Boy. We have to pick something to represent our U value here. If you pick the denominator and differentiate both sides, you get that du equals the quantity 3x squared plus 3 dx, where you can pull out a greatest common factor of 3, divide that over to the left side, and now I have a plan to substitute. My whole numerator can be rewritten as x squared, 1/3 du. So in my new line, I have a 1/3 du. The denominator is going to be just a u to the third, so u to the third, and you would take the antiderivative the same way we always have, and you get choice D, layup. Number 5, the function f is given by f of x here. On what intervals is the graph of f concave up? Anytime I hear concave up or concave down, I know I need my second derivative. So we take the derivative of this to get f prime, take the derivative of that to get f double prime of x. And I definitely want to set this equal to 0 to find the times when I might have a point of inflection, a change of concavity. We can factor the right side by pulling out a greatest common factor of 12x. and I find that x can be 0 or 2 to get a possible point of inflection. So on a number line, I like to think about, well, okay, at 0 and 2, I know the second derivative is 0, but what is it in between these values? I plugged in 1 to my second derivative. I'm not allowed a calculator, but I know 24 minus 12 will give me something positive. I plugged in 3. I know that cubing 3 and then 12 times that will be a bigger value than 24 times 3. It ends up coming out negative. Same result here with f double prime of negative 1. This tells me the only time it's concave up is between 0 and 2. I check that one, and that's a layup. If, for example, this problem was asking for a point of inflection, I know 0 is because it does change from negative to positive, and 2 is because it changes from positive to negative. It's possible for you to have the second derivative equal 0, but it not to be a point of inflection. Just a little side note there for number 5. Number 6, I have this implicit equation with x's and y's living together on one side of the equation, and really y's on both sides. What is dy dx at the point 2, 8? So I take this and I take the derivative of this whole expression. The derivative of x with respect to x is dx dx, and that comes out to 1. Here I have 3. 1/3 comes out front. I remove 1 from the exponent, and then the chain rule states the dy dx is dy dx. This could be one thing a lot of people will forget when they take the derivative with respect to x. Dx dx is 1, and I'm done. But dy dx is dy dx, and that's exactly what they want to know about. So make sure you keep this term in here. And on the right side, the derivative of y with respect to x is the derivative of y with respect to x, dy dx. All you have to do is plug in 2 for all your x's, 8 for all your y's, and solve for dy dx. And I'm sure if you follow along with my work here, you'll see how I got, I think it was 4/3 for dy dx. Number 7, this is one where I have to take the derivative of x to the 5th. No problem, that's 5x to the 4th. Then the derivative of 5 to the x. Notice these are very similar, but quite different. This is one of those rules that we don't use often, and it ended up being on a few AP exams in the past. Here's the rule you need to remember, and it's the whole reason I would say this is not quite a layup. This could be a 3-point shot. The derivative of some constant to the x is that constant to the x times the natural log of a. We derived this once we started to use the chain rule together in class. Really, all you have to do is rewrite this and then put the natural log of that constant, and you pick choice D. But I think with us not using this one as often, I wouldn't say this is a layup. I called this a 3-point shot. Number 8, when I have to run a limit as x approaches infinity of this rational function here, what I like to do is plug in infinity and see what happens. And if I get some indeterminate form of infinity over infinity or 0 over 0, I'm going to run L'Hopital's rule and try this again. So here's what L'Hopital's rule says to do. Take your numerator, take the derivative of your numerator, take your denominator, take the derivative of your denominator, rewrite your rational function with those new derivative functions, and try it again. And so, okay, I'll plug in infinity and infinity, and it happened again. So we run L'Hopital's possibly more than once. We have to use it actually twice here. So I go again. Derivative of the top, what's nice is it goes from a degree 2 function to a degree 1 function to a constant. So there's nowhere I can plug infinity up there anymore. I know this is my final step. The denominator doesn't change at all. That's okay. That's how E works. And when I plug in infinity here, my denominator gets very, very big. In fact, it's a very, very big positive value. Just remember, when your denominator gets very, very big, your fraction approaches 0. You pick choice B. All good. 2 L'Hopital's. Number 9, let R be the region bound by the graphs of y equals 2x and y equals 4 minus x squared. What is the area of R? I know you might not do this one graphically. I like to visualize these. So here in the red is just a linear function. If I rewrite this, I know it's a degree 2 polynomial with a negative leading coefficient. This is a downward facing parabola. So what you could do is find their points of intersection. I did that right here and found that they intersect at 0 and at 2. And so I can, when I write my limit, when my integral, I have the limits from 0 to 2 as my intersection points. All you have to remember is top minus bottom. You can simplify this and then just take the antiderivative. Make sure you plug in 2 and plug in 0 and subtract the results. And I think you all can handle this one to get 4/3 on your own. Layup. Number 10, the graph of the function f is shown above. If g is the function defined by this rational function, what is the value of g prime of 2? Before I even evaluate g prime of 2, my question was, what is just g prime of x? So here I have g of x as some sort of function on top, some function on bottom. And remember your product and quotient rule, where if you have a rational function like this, or you can write it as a over b, your quotient rule says you're going to do the derivative of a times b minus a times the derivative of b divided by b squared. So we'll do this one at a time. A prime is the derivative of my numerator, which is going to be 2x. B, I just write f of x. Minus sign comes down. A is just my numerator, so x squared plus 1. B prime is the derivative of your denominator, which is just my f of x, so f prime. And then it's the denominator squared. My denominator is f of x, so we get f of x quantity squared. I now plug in 2, really anywhere there was an x, and I simplify. And for some of these, it's very easy. 2 times 2 is 4. F of 2 is 3. This comes out to 5. F prime of 2 is looking for the slope at 2. So how steep is this line? You can always do rise over run to see that it's up 4 over 1 for a value of 4. And then my denominator, f of 2, was 3. 3 squared comes out to 9. You simplify this, and you pick choice A, layup. 11, I'm looking for an antiderivative. There was one thing we learned back when we started to do area under the curve, and it's that sometimes there is a very thin line or a moment when your function doesn't exactly exist. This is a function that has a hole at 0. And so you, if you pull that greatest common factor out and cancel it, you have just the function x minus 1, a linear function with a hole at 0, negative 1. You can still integrate this. If you're unconvinced that you can integrate with a hole existing, you're welcome to split this up as the integral from negative 1 to 0 and 0 to 1 and combine those together. But here's the work for me just integrating it the same way they wrote it, but I simplified to this x minus 1. You end up with negative 2. I think this one could be a layup. It could be a 3-point shot. I think it's subjective, but I left it as a 3-point shot. 12, we have a table. The table above gives selected values for the differentiable function f. In which of the following intervals must there be a number c such that the slope of c is 2? This is your mean value theorem. I need to really one by one check these and see what is the slope along that interval. So from 0 to 4, you just do rise over run. It's over 4 and down 8. We call this a slope of negative 2. Those aren't the same value, so I cross that one off. Really, the only one that gives you a slope of 2 is c. And here's what your mean value theorem says. From 8 to 12, the average slope here is 2. And the mean value theorem guarantees somewhere in this interval, if it's continuous and differentiable, you have a slope of 2 somewhere in between 8 and 12 in this case. And they say that we have a differentiable function f, therefore it's continuous. Everything is met for me to pick 8 to 12, choice C. 13, another L'Hopital's. I hope the work will explain itself. We did one of these before. Absolute layup. 14, a particle moves along a straight line so that at time t greater than or equal to 0, its acceleration is given by this acceleration function. At time t equals 0, the velocity of the particle is 2. I make a note of this. At this time, the velocity is 2. So v of 0 is 2. And the position of the particle is 5. I make a note of this. At this time, 0, the position is 5. Which of the following is an expression for the position of the particle at time t greater than or equal to 0? Here's some things I know about position, velocity, and acceleration. The derivative of velocity is acceleration, so you can go backwards and say that velocity is the antiderivative of your acceleration. And I plug my acceleration model in and take the antiderivative, and I, alongside you, will not forget our plus c. You can use your initial condition, one of the two, to find what that c value is. Here's my velocity, and I don't know what c is, but I do know that at time equals 0, the velocity is 2. And you can solve for c to be, in this case I called it c1, to be 2. So here's my new velocity model, 6t squared plus 2. And we go again. I know that the derivative of position is velocity, therefore position is the antiderivative of velocity. I plug in my new shiny velocity model, take the antiderivative. I, alongside you, am not going to forget this plus c. I have an initial condition for my position where at time equals 0, so I plugged a whole bunch of zeros in here. My position is 5, and you solve for the next c value to be 5. Here's your position model. You pick choice D. This is the halfway mark. Let f be the function defined above. Which of the following statements about f is true? We are talking about continuity and differentiability. It's a piecewise function, so if there's any gaps or jumps, I possibly might not have a continuous function, and if there's any sharp points or cusps, I might not have differentiability. So there's two things I want to check. First, for it to be continuous, I want to make sure that the first line ends where the second line starts. So I'm going to plug 5 into each of these, and the algebra for this is very easy. You get the same value. So the top one ends at negative 22. The second one starts at negative 22. I have one of them including 5, one of them being just after 5. Therefore, my function is continuous. And I've narrowed it down to one of them that does talk about it being continuous. To know if it's differentiable, you need a nice smooth curve at 5. I need the slopes to be the same around 5. So I'm going to find f prime of x for both of these and plug in 5. If you take the derivative of your numerator, you get negative 2x. You plug in 5, you get a slope of negative 10. When you take the derivative of the denominator, you get negative 10. And then you plug in 5 nowhere, and you get negative 10. So the steepness matches and the height matches. I can declare that it's both continuous and differentiable. Be ready to pick something where it might not be continuous or it might not be differentiable. You want to check both. If dy dx equals 2 minus y, and if y equals 1 when x equals 1, then y equals one of these. Okay, let's take this one step at a time. I'm just going to rewrite this differential equation. I'm going to separate and integrate. So what I'm going to do is multiply dx over, divide by 2 minus y, and take the antiderivative of both sides. This will, in a way, give me a function with no dy dx, no derivative functions, just my y's and x's for a particular solution. When you take the antiderivative of 2 minus y, a negative is going to show up in front. The reason why, and we did this back in the notes, is when you do use substitution, when you change this dy, you get a negative du. So just keep in mind, if your variable is negative, a negative will show up. But if instead this was y minus 2, it just becomes the natural log of the absolute value of y minus 2. So keep an eye of where your variable is. If it's positive, don't worry. If it's negative, bring a negative along with you when you anti-differentiate. Here I put a 1. The antiderivative of 1 is x, and I, alongside you, will not forget plus c. Here's where I have highlighted these coordinates, where I plug in 1 for x, 1 for y, and I solve for my c value to be negative 1. Here is a particular solution for this differential equation. I just have to solve for y. I would recommend removing this negative by multiplying both sides by negative 1, raising both sides to be the exponent of e. E to the natural log of 2 minus y gives me 2 minus y. On the right side, I kind of kept this the same and just subtracted the 2 and multiplied by negative 1. And you'll notice that choice B shows up. I would not call a differential equation with separating and integrating a layup problem. This is absolutely a 3-pointer, so be ready for that. 17. Let g be the function given by g of x being the area under the curve from 3 to something of this equation in terms of t dt. What is the x-coordinate of the point of inflection of the graph of g? There's a lot of words here, so let's go one step at a time. I need to know the point of inflection for g. So point of inflection, I know I want to find the second derivative of g. So here's g. Let's take the derivative of both sides to get g prime, and then the derivative again to get my second derivative. Using your fundamental theorem of calculus, when you take the derivative from a constant 2x of some function in terms of t dt, you just get that function with x's in place of those t's. I get here that g prime of x is just this, but notice I bring x's along for my new equation. When you take the derivative again, I just get 2x minus 5. I want to know what x needs to be to get 0, and that ends up being 5/2. I want to first double check that it is a point of inflection, so I'm going to, with my second derivative, plug in something left of this and right of this, and with it being 2.5, I just did 2 and 3, found that one of them is negative, one of them is positive. We have a point of inflection at 2.5 or 5/2. 18 is a product rule problem, where again it's a prime b plus ab prime. I have my a value being x cubed, my b value being secant of 2x. I think product rule problems should be a layup. The only reason this one is not is because you might not remember the derivative of the secant of 2x. The derivative of the secant of x is going to be secant tan. The rule is there's always two secants, one tangent. So the derivative of tangent is secant squared. The derivative of secant is secant tan. Alongside that, with it being 2x, you have to incorporate a chain rule. And altogether, for whatever reason, this comes first, this comes second. You get choice D. So be very careful simplifying this. It's just a product rule. It could be a layup, but it is in a 3-point shot for my ranking. A particle moves along the y-axis so that at time t greater than or equal to 0, its position is given by this. Which of the following statements describes the motion of the particle at time t equals 1? I have my y position at a specific time, and if I take the derivative of that, I have a function known as velocity to tell me maybe which direction I'm heading at different times. And so you just take the derivative of this and you get your v of t. I want to know what's happening at 1, so I plug in 1 here. I notice that 3 minus 8 plus 4 is something negative. Right away, if your velocity is negative, you are either heading, in this case, down or up, negative being down. If it's the x-axis, you are heading left. So right away, from me knowing that the velocity at this time is negative, we are moving down the y-axis. That narrows it down to a or b. If you look at the derivative of velocity, it's acceleration, which describes the steepness of velocity, the slope at that time. It ends up being negative. If this was asking if we are speeding up or slowing down, you are looking for matching signs. Notice it is not asking that. This is just the slope of my velocity. And if my slope is negative, we say that a function is decreasing. So I specifically need something where I am moving down the y-axis and my velocity is decreasing. And choice A has both of those. Be very careful on the wording there. If the integral from 1 to 4 of f of x dx is 8, and the integral from 1 to 4 of g of x dx is negative 2, which of the following cannot be determined from the information given? For number 1, I don't have something with these bounds, but you can always rearrange this if you have a negative put in front of your integral. And so the first one's absolutely fine with my rules of integration. For b, there's a 3 value that I can pull out front, and then I can integrate this just fine. I know what this value is. I'm going to skip c for a second. D is something where you can separate it into 2 separate integrals, and this 3, like choice B, this 3 can be pulled out. I do know the integral from 1 to 4 of f of x and the integral of 1 to 4 of g of x. I, by deductive reasoning, can evaluate a, b, and d. The product of these is not something I know a lot about, and I know that with addition and subtraction I can split this up into 2 integrals, but not with multiplication. We are not able to evaluate c with the given information. 21 looks at the definition of the derivative, where it's the average rate of change of your function plus h minus your function over x minus, it's h minus x minus, it comes out to h. Down here, it's some sort of change in distance, and it's the limit as this h value approaches 0. It's basically looking for the slope of two coordinates that are incredibly close together to get that instantaneous rate of change. All you have to look at is up here. This is the function we're working with in your average rate of change equation. All you have to do is take the derivative of that. And so it is a cosine of 2x. Do not forget your chain rule. You pick choice D. You can ignore literally all of this. You just need the derivative of that top right portion. Here we have a slope field. Shown above is a slope field for which of the following differential equations. There's one with absolute value, there's an x cubed, a y cubed, and a y squared. I would recommend as many coordinates as it takes, try a coordinate and see if the slope matches the picture. I'll give you some examples. I tried the coordinate 0, 1. So 0, 1 is right here. And I would say that the slope is positive. It almost looks like a slope of 1. So if I can get 1, that's great. I'm really just looking for something positive. And right away, if I plug in 0, 1 to the first, I get something positive. Into C and D, I get something positive. But if I take 0 and raise it to the third, I get a horizontal slope, or a slope of 0. So right away, B is out of the race. I then tried negative 1, 1, really just moving 1 to the left. Negative 1, 1, I again get a slope that's positive. This is one where the first equation is going to fail because negative 1 plus 1 gives me 0, which does not give me something positive. A is out of the race. C and D move on. I plug in a y value of 1, squared or cubed is going to give me something positive. I need something that's going to differentiate both of these. I know that with one being even, one being odd, let's give it a negative y value to know for sure which one's going to win. So 0, negative 1 is this coordinate. I should have a slope that is positive, and the only one that gives me that is when I square a negative value, not when I cube it. C is out of the race. You pick choice D. 23, the base of a solid is the region in the first quadrant bound by the y-axis, the x-axis, y equals e to the x, and the vertical line x equals 1. For this solid, each cross-section perpendicular to the x-axis is a square. What is the volume of the solid? One thing to keep in mind, you can always do an xy table for this one. Just remember that when x is 0, e to the 0 is 1. That might help you see that it's a bit off the x-axis. But you don't even need to know that. You don't have to graph any of this. Just know that your exponential function is on top the whole way down, and the bottom is the x-axis for when I do top minus bottom. When you get a shape, all you need to know is the area of that shape. So if I have a square, I know the area is one side squared. Here, for example, might be one of those squares, where one side is just the length of this specific point. So I say that the volume is the integral from 0 to 1 of the area being one side squared, and one side just being top minus bottom. It comes out to be e to the x. Using your rules of exponents, 2 times x gives me 2x. This is one where if it's anything besides e to the x, you want to run u substitution. Shout out to Soulja Boy, where I pick my exponent to be 2x, take the derivative of both sides, and I end up with a 1/2 du replacing my dx. I go full u land here. And if you integrate this one step at a time, you should get choice B. I think a lot of the work here is a layup worthy problem, but remembering the area of the square is just so hard. I had to put this in the 3-point category. No, you're going to forget u sub or something similar to that is the main reason here. 24. The graph of the piecewise linear function f is shown above. What is the value of the area under the curve from 0 to 12 of f prime of x dx? This is a fundamental theorem of calculus problem. There are a handful of these on here where you just say the area under the curve from 0 to 12 of a derivative function is the antiderivative of this, which is just f. I drop the prime. evaluated at my upper bound minus my lower. And from the graph, you can find these very easily. F of 12 is negative 4. F of 0 is 4. Subtract the 2 and get negative 8. This one looks a lot kind of difficult to set up, but being a fundamental theorem of calculus problem, being this simple, this one is upgraded from a layup to a slam dunk. There are a handful of slam dunks on here, so be ready for those. You all will get this one. 25. The equation y equals 2e to the 6x minus 5 is a particular solution to which of the following differential equations? You want to find the first derivative and possibly the second. If I can avoid finding the second for time purposes, I will. So I take the derivative of both sides to find y prime. It comes out to being 12e to the 6x, and then I just try this one out, where in y prime, I plug in my y prime that I found. For y, I plug in the y that was given, and just see if it works. And you hope that the question writer had maybe one of the first ones you try working. It ends up that A just works here. You end up with 12e to the 6x minus 12e to the 6x, poof, plus 30 minus 30, 0 does equal 0. If these first two do not work, take a second to find your second derivative and evaluate C and D separately. This one could take some time, so really hope it's one of the first ones you try. 26. What is the value of x? What is the value of x at which the minimum value of this function occurs on the closed interval 0 to 1? If I ever need a minimum of something, I'm looking for the first derivative. So what I'm going to do is take the derivative of both sides. I'm going to find y prime and set it equal to 0. So y prime is equal to, well, just the derivative of this. I want to know when this derivative equals 0. The algebra to get this could be a bit tricky. I just add the 2, divide by 4, cube both sides, and I get 1/8 as a candidate. You don't see 1/8 and pick 1/8. It is possible that this is not the minimum on this interval. You also have to check your endpoints. And it's very possible the question maker might have an endpoint be a lower value than this time. This is when my slope is 0, but it might not be the lowest on this interval. You want to check 0, 1/8, and 1. I just plug them back into my initial function, and you pick the lowest one. So we start off at a height of 0. At 1/8, I'm at a height of negative 1/16. And at 1, I'm at a height of 1. This is the lowest value, therefore it is our minimum. Be very careful with this. I still keep it in the layup section, but be wary. 27, at time t equals 0, a storage tank is empty. I keep this in mind. I might need this information later. And begins filling with water. For t greater than 0 hours, the depth of the water in the tank is increasing at a rate of W, feet per hour. Which of the following is the best interpretation of the statement W prime of 2 is greater than 3? So I made a note of this. I said, well, W is already a rate. W prime is the rate of a rate. So when I'm looking through this, I'm really looking for kind of rate of a rate language. 2 specifically says the time that something happens. B talks about over the first 2 hours. I'm looking for a very specific time, so I'm not picking B alongside D. They don't incorporate this 2 well. This 2 really means that at the time 2, or 2 hours after we started filling the tank with water, something happens with the level of the water or the rate of the water. So this narrows it down right away to A or C. Then I'm looking for a specific time, what's happening there. Specifically that W of t is a rate, I need something that says that the rate is increasing because I have a positive value here. Notice that C and D at some point talk about a rate increasing. So this is one of the things I'm really looking for. The only one that includes the time of 2 and a rate that's increasing is choice C, and you pick choice C. We'll read it out. 2 hours after the tank begins filling with water, the rate at which the depth of the water is rising is increasing at a rate greater than 3 feet per hour per hour. Here's a real language for rate of a rate per hour per hour. 28 is one of the 2 half-court shot problems. And yes, you can get a half-court shot, but it's not easy. So they nicely have an illustration for us. Let's read through 28. A person stands 30 feet from point P and watches a balloon rise vertically from the point as shown in the figure above. The balloon is rising at a constant rate of 2 feet per second. I highlighted this and made a note of it, and I ended up using that later. What is the rate of change in radians per second of angle theta at the instant when the balloon is 40 feet above P? This is also something I'm going to end up using. You first want an equation that relates an angle theta and the height of the balloon. And with the information I was given, I just thought to do, well, opposite and adjacent. I did tangent. So using SOHCAHTOA, the tangent of an angle is opposite over adjacent, h over 30. If you take the derivative of both sides, the derivative of tangent of theta is secant squared. The derivative of the inside is d theta dt. This is one thing a lot of people will forget. The chain rule brings us along for the ride. Dividing by 30, I wrote as 1/30th, and the derivative of h with respect to t is the derivative of h with respect to t, dh dt. Here's where I kind of stared at this one, and I was like, okay, I need the height to be 40. And here there's nowhere to plug in h. I do know dh dt is going to be 2, so I was pretty confident about pairing those together. But there's nowhere to plug in the height. And so to the side, I just redrew this and said, well, what if I make this distance 40, and this distance has always been 30, what would my hypotenuse be? This is one of your 3, 4, 5 Pythagorean triples. You can also run the Pythagorean theorem to convince yourself this is 50. And so I can declare that the secant of theta, with cosine being adjacent over hypotenuse, this is hypotenuse over adjacent, and it simplifies nicely. So I used this value to create an equation where I could rewrite my secant as 5/3 and then substitute that in. 5/3 squared is 25/9. The change in height per change in time was 2. You just solve for d theta dt and end up with, I think it was 3/125 radians per second. Feel free to convert this to degrees if that makes a bit more sense contextually for you, but in terms of radians, this is what we got. We picked choice B. Definitely one of the hardest ones on this practice exam. Only 2 more to go for the non-calculator portion. This is a pre-calc question. How many vertical asymptotes does this graph have? Difference of squares for your denominator. Difference of squares again. Anytime you get a factor canceling, this creates a hole. A hole is different from an asymptote, so be wary of that. Any value that your denominator still can't handle, like a -2, this creates a vertical asymptote at x equals -2, and it's the only vertical asymptote. Last one for the no calculator section. For what value of b does the integral from 1 to b of x squared dx equal the limit as n approaches infinity of the summation from k equals 1 to n of 1 plus 2k over n quantity squared times 2 over n? This is another half-court shot problem. If you see this and get a bit scared, there's 2 things you need to remember. We worked with this when we derived what an integral is. This is a fancy way of writing an antiderivative, and it ends up being exactly this. Let's talk about how we get to here. You're going to have in 2 separate places in your definition something to represent b minus a over n, a and b being your limits of integration. It turns out that b minus a is 2. So I made a note of this. I said, okay, b minus a is 2. Inside here, you're going to start with a, go a little bit of delta x over, and then evaluate it to, kind of add up all of these different heights. So a is going to be inside there. A's got to be 1. And if I plug 1 in, it tells me that b needs to be 3. So my limits of integration are a being 1 and b being 3. Now you need to know what function you're integrating. Really, you can just cross off everything you know about. I know this is a. This is my b minus a over n. This is my b minus a over n. It's something squared, specifically x squared. And so they're just asking, hey, what does b gotta be? You can really see the symmetry here. B's gotta be 3. My upper bounds have to match here. you choose b equals 3 only. That could be a very difficult problem if you see this and get a bit scared, but I hope us talking about this one will help you be a bit more prepared to approach a problem like this. We have 15 more to look at. In the next video, we're going to bring out a calculator and tackle those.